So we spent not very much time on infrared because infrared is really, really good for identifying compounds that contain oxygen and to a lesser extent nitrogen, but then anything else, if you've got available NMR or mass spec, you'll move to those. But it is worth spending just a little bit of time on the 10 spectra and 10 different compounds that were there in the worksheet, just illustrating how I would go about using infrared spectroscopy under these conditions. So we'll start off with the first set of compounds in which I had 5 spectra, A, B, C, D, E, of which A and B are here, and compounds 1, 2, 3, 4, 5. And what you'll notice is compounds 1, 2, 3, and 4, 5 all have oxygen in there. And that's pretty much the only interesting things about them, except compound 1 also has this carbon-carbon double bond there. So let's look at spectrum A and see what we can do to distinguish between whether it is for 1, 2, 3, 4, or 5. So first thing I will always look for in an infrared spectrum is I will look up in this big area here that's associated with the bonds to hydrogen. Now you've got your carbon hydrogen bonds there that of course will be present in every single organic compound, and those will have the various bends and stuff down here as boring. But what's significant about spectrum A is that there is not a nice big broad peak associated with OH. So in other words, the lack of OH means it can't be compound 1, can't be compound 4, can't be compound 5. Okay, now the next thing I'll look at is in this region here. Is there a nice sharp dominating peak there somewhere between about 1650 and 1800, give or take? And indeed here there is that beautiful dominating peak that corresponds to a carbon oxygen double bond. Okay, so the two big regions up here, which in this case we don't have, and here, which in this case we do have. So no OH but a carbon oxygen double bond. That pretty much allows me to distinguish this as compound 3. Okay, so spectrum A goes with compound 3. Now let's go to spectrum B, which is the most boring of all. First of all, no OH. Secondly, no C double bond O. Massive bunch of crap down here, right, that I'm sure if I was a big infrared person I could tell you some things about here. Obviously the carbon oxygen bonds are floating around in here, carbon oxygen single bonds, various other bends, vibrations and so forth, but we don't really care too much. If I wanted to worry about this, I'd go find an NMR. What I do care about is that spectrum B, no OH, no C double bond O. Thus that means of these 5 compounds it has to be compound 2. Now that's as good as it gets for infrared in these type of compounds, unless you really delve deeply into it, but it was good enough to enable us to identify compound 2 simply by process of elimination. Moving on to C and D, knowing of course that we already got rid of compounds 2 and 3. Let's have a look at compound C. What leaps out at you? Well, I trust that beautiful OH peak right there. Very, very diagnostic. Nice broad hump down there, sort of 32, 3300. Gain CH here. Don't really care too much about that because they're going to be there in everything. And then what we do not have in compound C is C double bond O. So let's find something that has no C double bond O but does have an OH. And what we got there is we got compound 1 and we've got compound 5. Okay, well the one thing that we can look for as far as carbon-carbon bonds are associated in the infrared spectrum is carbon-carbon double bonds and carbon-carbon triple bonds. The carbon-carbon double bonds occur in this sort of carbon double bond to something region, and carbon-carbon triple bonds would occur up here in the carbon to triple bond something region. Okay, so not only here is there no carbon oxygen double bond, but there's also no carbon-carbon double bonds, so nothing there. So I'm going to suspect strongly that spectrum C does not correspond to compound 1, and it does not correspond to compound 4 because there's no C double bond O peak there, so it's probably 5. But let's confirm that by going ahead and looking at spectrum D. Spectrum D has the OH in there. Of course, all 3 remaining ones here have got OHs in file 5, 4, and 1. Okay, so there's the OH we'd expect. There's no C double bond O, but spectrum D does have this nice sharp peak right here in that carbon-carbon double bonded region. So I would go ahead and say that's my carbon-carbon double bond. Thus, compound 1 corresponds to spectrum D because it's got the carbon-carbon double bond, and spectrum 5 compound 5 corresponds to spectrum C because there is nothing in that carbon double bond something region. Okay, so a little bit tougher to distinguish between C and D, compounds 1 and 5, but the way you can do it is, again, both of them have the OHs, both of them have this big mess around here where you'd expect carbon-oxygen single bonds to be, but spectrum D had that extra teensy little peaky spike bit there that's that carbon-carbon double bond. Finally, of course, we better hope that spectrum E corresponds to compound 4, otherwise we'll have to go back and do something else. And indeed it does. First of all, we've got this big messy bit down here, which is an acid OH. Remember, the acid OH comes at a lower wave number than the regular OH, which would be sort of here. It's also why they're yuckier and nastier, but that's the acid OH. And then, of course, the very distinctive C double bond O peak there, smack at about 1700, 1710. Combination of the OH and the C double bond O would at any point during question 1 have identified quite nicely compound 4, the acid. Okay, so overall, there's the answers for compound 1. Question 1, I should say.